In the previous video, we talked about finding a dilated graph of the given figure by using the origin as the center point of dilation. However, in this example, I'm going to use the same coordinates and the same starting shape. The only difference is the k value will be positive and the center of dilation is not going to be the origin this time. It's going to be the point 4, 5. So I'm going to show you two ways to find this dilated graph, namely the triangle in this case, the algebraic way and the graphical way. The first way is going to be the graphical way. So let's plot the center of dilation point. So we already have the triangle plotted, these 3 points, these 3 vertices. Now the center of dilation point is going to be 4, 5, right, in quadrant 1. So it's going to be right here. So the first way I'm going to show you is the graphical way. The way to understand this is that recall that when you were dealing with the center being the origin, the distance from the origin to each vertex was increased proportionally by the value of k. Okay? So for example, if you use the k value of 2, the distance from the origin to each vertex would increase by 2, by a factor of 2. Okay? So each distance to the respective vertex, you would have to multiply that distance by 2 and extend that distance further. Okay? So in the same manner, even when the center of dilation point is not at the origin, you still have to track the distances and make sure that your distance increases by 2 to each vertex, and that will be your respective new vertices of the dilated graph. Notice that we're making this triangle bigger because the scale factor, the absolute value, is greater than 1, right? It's 2. So let's think about how we can think of the distances. Notice that this distance, you might think, oh, it's kind of hard to pinpoint the distance because it's not a horizontal line, it's not a vertical line. However, you can think of components. For example, notice that you're going 1 down and you're going 1, 2, 3, 4, 5, 6. So that means if you're using the scale factor of 2, you will have to go 2 down, right? Because 1 times 2 is 2. And then here you were doing 6 to the left horizontally, so you have to go twice that, which is 12, right? So you go 2 down and 12 to the left. So another 6 from here, right? 1, 2, 3, 4, 5, 6. Okay? So that will be the new point. So 6 more from here. 1, 2, 3, 4, 5, 6. That would be right here. So that should be your theoretical A prime. Now, in the same manner, let's talk about distances to the vertex C and to the vertex B. Notice that C, we're kind of lucky because we can actually create a diagonal line through these respective corners and get from this point to this vertex, right? Notice that we can actually use the corners here, okay? And let's think about how many corners we covered. 1, 2, 3, 4, 5, 6, 7. So if you multiply the 7 corners, the distance of 7 corners by 2, the scale factor, that means we have to keep going diagonally 7 more because we're going to have a distance of 14, right? Twice that. So let's go 7 more from here. 1, 2, 3, 4, 5, 6, 7. Okay, so this should be the C prime vertex. And now in the same way here, notice there are no corners anymore because you're kind of skipping corners each time. It's not a diagonal line. However, you can use components just like you use for the A, right? So let's think about the components. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9 and 3. So that means you have to multiply each component by the scale factor of 2. So if you're going down 9, you need to go 18 overall, so 9 more from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's plot a point here. We barely made it out of the graph, but you can see there's one more. This is one more step, and this would be the point that you're at. And then you needed to go 3 to the left from here, from this vertical line, right? So that means we need to go 6 altogether, right? So 3 to here, as should be to the B, and also additional 3, right? Because we're multiplying the distance by 2. So we need 3 more. 1, 2, 3. Okay, so let's erase that point. And we're going to be winding up here, right? So that would be the B prime. Okay, so that would be the B prime. And now let's connect those points, actually, because now we can do that. Let's connect them, and then I'm going to show you how to verify this result using the algebraic method. Okay, so let's connect this triangle, and you're going to see that there is indeed parallelism, as it should be, between corresponding sides of this of each of these triangles. So notice that B prime C prime is parallel to BC. Okay, A prime B prime is parallel to AB, and A prime C prime is parallel to AC. These sides, right? So parallelism is maintained no matter what the center of dilation point is. It's the origin, it's not the origin. The dilation makes sure, whether you make it smaller or bigger, that there will be parallelism intact. Okay, parallelism never goes away. So now notice that we've used the graphical way. Now let's use the algebraic way. How would you do this algebraically to confirm that these are indeed the correct points or correct coordinates? So I'm going to use the coordinates this time, and I'm going to show you how to verify this. Okay, so using the coordinates, what you're going to do for the A prime, starting A prime, you're going to multiply the scale factor by the x coordinate. So you're going to do minus 2k, and then you're going to subtract from this the x coordinate of the dilation center point, so minus 4. And the same thing for the y coordinate. You're going to multiply it by the scale factor, 4k, right? 4 times k. And then subtract from it the y coordinate of the center of dilation point. Okay, so let's verify this. This is what we get. Negative 2 times 2 is negative 4. Negative 4 minus 4. And then here we get 4 times 2, that's 8. 8 minus 5. So let's see what we get. As a result, we get minus 8 and 3. Does it make sense for the A prime? Let's check it. Minus 8 from the origin, right? 1, 2, 3, 4, 5, 6, 7, 8. Good. And then 3 up, right? Because that's the x coordinate. Look where we wound up. We wound up right at the shown A prime point, just as we speculated using the graphical approach, right? So algebraically, this is still correct. It verifies that what we plotted is correct. Now let's use the same technique for the B prime and C prime just to make sure that we got everything correct. So for the B prime, we're going to get, and again, the same thing. You're going to multiply the x coordinate by the k, so that's k. 1 times k is k. And then subtract the x coordinate of the center of dilation point. Same thing for the y. So we're going to go minus 4 times k, so minus 4k. And subtract from it the y coordinate of the center of dilation point, minus 5. So what we're going to get is k is 2, 2 minus 4. And then here we get 2 times negative 4, that's negative 8, right? 2 times negative 4, negative 8, minus 5. And let's verify that. We get 2 minus 4 is negative 2. Negative 8 minus 5, negative 13. Let's verify that. So B prime is here. So negative 2, so far the x coordinate is correct because this is negative 2. And then down negative 13, down 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Bingo! The correct point, right? So the graphical B prime matches the algebraically verified B prime point. So now let's take care of the last one and then we're done. So again, here we're going to multiply the negative 3 by k and then subtract the x coordinate of the center of dilation point. Okay, and let me just write this down that this is the center of dilation, just so you know, just so you don't forget. And then here we're going to have negative 2 times k and subtract from it the center, the y coordinate of the center of dilation point. So we're going to get negative 3 times 2, the k value is 2, that's negative 6 minus 4. And here we get negative 2 times 2, negative 4 minus 5. And as a result, what we get is -10, -9. Let's verify that for the C prime. -10, so 10 to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Beautiful. And then -9, so 9 down. 1, 2, 3, 4, 5, 6, 7, 8, 9. Bingo. So all the 3 vertices are plotted correctly using the counting graphical way that we've done by basically multiplying the original distance to each vertex from the center of dilation point by 2 and arriving at the correct vertices of the enlarged dilated triangle. And also we verified that result by using the algebraic formula, okay, that I just told you about. So I hope this was useful and fun. I had a lot of fun with this. I hope you did too. And I'll see you in the next video. Thanks for watching.